Hey everyone, welcome to more stats fun today with me, your stats teacher. We're going to be taking a look at the Chapter 3 practice test, or at least the first 4 questions of the Chapter 3 practice test. So let's go ahead and get started over on our next screen. A researcher wishes to determine whether the rate of water flow in liters per second over an experimental soil bed can be used to predict the amount of soil washed away in kilograms. In this study, the response and explanatory variable are, maybe a good place to start this would be to think about what are we trying to predict. And lucky for us, the word predict is right in our question. So if the word predict is right in our question, then that should tell us that whatever we have here, which is the amount of soil washed away in kilograms, that's going to be our response variable. Next, we're trying to say, well, what is affecting that response variable? What is affecting the amount of soil washed away? And what we see here is the rate of water flow is going to be used to predict. So that tells us that the explanatory variable is going to be the rate of water flow in liters per second. So that's great. Let's take a look at question 2. Consider the scatter plot in graph 1, which describes a relationship between stopping distance and air temperature for a certain 2,000-pound car traveling at 40 miles an hour. Estimate R, the correlation coefficient. It's important to know that with this question, there is no right answer. There's just a range of values which could be correct. Now, I'm going to zoom in here on graph 1. And what I notice is, yes, I can see a line here. It's kind of, I always think of the scatter just kind of clouding around the line. So I can see, right in this area, if I do that, I can see a line, or maybe a band would be a good way to talk about this. So if I kind of draw boundaries for where most of the points are, now there's a couple of these that are not fitting very well, but notice how they are all kind of in this narrowish band. So if I see that, if I can group them together in a band that is pretty linear, then that would tell me that I have at least a moderate regression. If you draw this band and it takes up pretty much the entire graph, then you don't have a very strong regression. And then the closer those two boundary lines are together, the closer to 1 or negative 1 your R is going to be. In this case, slope is positive, so R should be greater than 1 or greater than 0. So we have a positive R. So any R that's greater than 0.5, I would probably say it's closer to 0.8. That would be pretty appropriate here. So let's just say R is about 0.65. That may or may not be what we put in the answer key, but it's kind of in the same ballpark. Certainly, the R is going to be positive because of the positive trend, but, this is a little bit not one correct answer. There's a range of values which could be appropriate here. Number 3, the height in feet and volume in cubic feet of usable lumber of 32 cherry trees is measured by a researcher as shown in graph 2 above. So we're going to have to look at graph 2. The goal is to determine the volume of usable lumber that can be estimated from the height of a tree. So we have a data point 6570, and we're going to remove it from the study. And how would the value of correlation change? So without looking at the question, I'm going to say that, well, if removing the point is going to create a tighter cluster, a relationship that looks more linear, then our value of r should get closer to 1 or closer to -1, depending on what we see on the graph, positive or negative trend. So closer to 1, closer to -1. And of course, if we remove the point and we get something which is less linear looking or less of a definite trend, then we're going to see something which is r is going to decrease. So let's try and find this 6570. Where is 6570? Okay, I think I see it. Here's 65 right here. Here's 70 here. Those two meet right about there, and look at that point. That is way far away from the rest of the scatter. Okay. We talked in graph 1 about that narrow band, and if I highlight that narrow band again, okay, notice how far away it is from that. So if I remove that point, that's just going to make the scatter tighter. It's going to make everything closer, not make it closer, but it's going to make the trend more obvious. Now the only other trick part here is, will it increase or will it decrease r? And based on the fact that we have a positive trend, that means that our value of r is going to get closer to +1. Getting closer to +1 means that r is going to increase. The opposite would be true if we noticed a negative trend, a line with a negative slope. The value of r would actually decrease because we're getting the value of r would get closer to -1. So it would have to decrease to get closer to -1. In any case, for this one, our value of r would move closer to +1, so our value of r would increase. Finally, we have number 4, which says that a researcher wishes to study how the average weight of children changes during the first year of life. He plots those averages versus age and decides to fit a least squares regression line to the data with x as the explanatory variable, remember x is age, and y as a response variable, which would be kilograms or weight. He computes the following quantities. R is 0.8, x bar 6.2, y bar is 6.4. We've got a value for sx and a value for sy. And so we want the equation of the least squares regression line. Lucky for us, we actually had the equation of the regression line in one of our big ideas boxes. It's right over here. It's 3.2 day 4. If I literally copy and paste that over, now I can start working on the equation. So the first thing we're going to look at is always slope, and I should probably spell that correct. So slope is equal to r times sy over sx. That's what we see here in this first equation. They give us all of those quantities, so when we substitute, we get ourselves a 0.267. Now the other equation I don't particularly like, and the equation that I prefer that we put in there, y bar equals a plus bx bar. Now I think that's better because that is just the regressional formula or the LSRL formula. So there's nothing new to learn here. The only thing new to learn is conceptually that the least squares regression line is always going to go through x bar, y bar. So all you have to do is substitute the numbers and then solve this algebraically. Remember, you're free to use any solving methods you like, graphing calculator, doing this analytically with pencil and paper. It doesn't matter to me. I'm not here to teach you algebra. We get ourselves A is 4.75 and that the predicted weight is 4.75 plus 0.267 times age. remember that this business with the word predicted weight and age in the formula, that is okay for anybody in statistics. Maybe your algebra teacher didn't like it that way, but in statistics, that's just fine. In fact, for me, that is preferable because you don't have to take the time to define what y is and what x is. You just write it. So please write your formulas in that manner, your least squares regression lines, with the word predicted weight and age. Don't worry about the y and the x. So that's it for our first video. We'll see you for the next one in a minute. Have a good day.